There is a planet, 140 million miles away, where the sky is the color of rust, where temperatures can swing from a mild spring afternoon to a freeze that would shut the human body down, all within a single Martian day. And yet, for the past 2 decades, one company has been working to send human beings there, not just to visit, but to stay. What we know so far is this: SpaceX has stated its long-term objective to build a self-sustaining colony on Mars. This is the story of how SpaceX will colonize Mars. But colonizing Mars is not a rocket problem. It's a survival problem. And every part of this plan depends on solving both. The machine is called Starship. It is the largest and most powerful rocket ever built. It consists of 2 sections: a massive first-stage booster called Super Heavy, and the Starship spacecraft that sits on top. Both stages are made from stainless steel. Both are designed to be fully reusable. The fuel is methane. That choice was deliberate. Methane is relatively inexpensive. It burns cleaner than other fuels, producing less soot in the engines. But most importantly, and this is what makes it uniquely suited for Mars, methane can be manufactured on the Martian surface itself. Mars has carbon dioxide in its atmosphere and water ice in its soil. Combine the two and you can make rocket fuel. A chemical process called the Sabatier reaction turns carbon dioxide and hydrogen into methane and oxygen. In other words, if you can get a rocket to Mars, and if you can mine the planet's water ice, you can theoretically produce the fuel needed to fly home. This is not speculation. The Sabatier reaction is established chemistry. What remains to be demonstrated is whether it can be done at scale, on another world, by a colony that is also trying to survive. The engines powering Starship are called Raptors. Each Raptor engine operates at pressures that are, by the standards of rocket propulsion, extraordinary. The projected cost per engine has been estimated at around $230,000 or, measured differently, approximately $100 per unit of thrust. That number, if achievable at scale, represents a fundamental change in the economics of space travel. The booster uses multiple Raptor engines. The spacecraft itself uses both sea-level Raptors and vacuum-optimized variants for travel through deep space. Each Starship is designed to carry 100 people. The transit time from Earth to Mars, depending on the position of the planets relative to each other, is estimated at between 80 and 150 days. On average, roughly 115 days. That is 4 months in a steel tube, in deep space, crossing a distance that makes the ocean look like a puddle. But here is the strange part. Even if the rocket works, even if the fuel can be manufactured on Mars, even if the funding materializes and the supply chain holds and the legal frameworks align, there is still the problem of the human body. And the human body was not built for this. What we know from decades of research aboard the International Space Station is that microgravity, the near weightlessness of orbit, begins to dismantle the human form almost immediately. Within several weeks, astronauts lose between 10 and 20% of their lean muscle mass. Bone density decreases at approximately 1 to 2% per month. The fluids in the body redistribute upward, filling the head, pressing on the eyes, causing changes to vision that can persist long after landing. The heart, no longer working against gravity, deconditions. The immune system shifts. There is a phenomenon now recognized as space anemia, a reduction in red blood cell production that occurs in the absence of gravity's demands. And then there is radiation. Beyond the protection of Earth's magnetic field, astronauts are exposed to ionizing radiation at levels that have no safe parallel on the ground. Over a long journey, this exposure increases cancer risk. It may affect cognition. It alters DNA. Mars has gravity 38% of what we feel on Earth. That is better than nothing, significantly better. But here is what the data suggests. Partial gravity at that level is probably insufficient to prevent serious physiological deconditioning over the long term. Indirect evidence indicates that below approximately 40% of Earth's gravity, the musculoskeletal and cardiopulmonary systems cannot maintain their conditioning. The benefit of gravity is roughly proportional to its strength. Exercise helps. But exercise, even extensive exercise, does not solve the problem entirely. A Mars colonist would face the same challenges. But unlike an astronaut, they would not be returning to Earth afterward. Artificial gravity has been proposed as a solution. Rotating habitats could simulate gravity, but no system of that scale has ever been built. And whether partial gravity on Mars is enough to protect the human body over decades remains unknown. Engineers have studied potential solutions. One approach involves artificial gravity spinning sections of a spacecraft at a carefully calculated rate to simulate the pull of a gravitational field. The physics are well understood. Rotation produces centrifugal force, and at the right combination of speed and radius, a person standing on the inside wall of a rotating ring would feel approximately the same as standing on a floor. But it is not that simple. Assume the journey is survived. Assume the body holds. What does a human being encounter on Mars? The planet's diameter is roughly 6,800 kilometers, just over half of Earth's. Its day is 24 hours and 37 minutes, almost identical to our own. And the sun still rises and sets, casting long shadows over an orange-red landscape of ancient craters, towering volcanoes, and canyon systems that dwarf anything on Earth. But the resemblances end quickly. The average surface temperature on Mars is approximately -55 degrees Celsius. At the equator, on a warm afternoon, temperatures can briefly reach 20 degrees. At the poles, they can drop to -153 degrees. The swing within a single day can be severe. The atmosphere, as noted, is predominantly carbon dioxide. Oxygen makes up less than 1% of the Martian air. On Earth, oxygen constitutes roughly 21% of the atmosphere. A human on Mars without a suit would lose consciousness in seconds, not from cold, but from the lack of breathable air and the crushing difference in pressure. The atmospheric pressure on Mars is approximately 9/100ths of what we experience at sea level on Earth. Standard pressure suits would be required at all times outside any sealed habitat. And then there is the soil. Martian soil contains perchlorates, a class of chemical compounds that are toxic to most plant growth and harmful to human health. Before any agriculture becomes possible, the soil would need to be either processed to remove the perchlorates or replaced entirely with imported growing media. There is also the radiation. Without a magnetic field comparable to Earth's, and with an atmosphere too thin to block high-energy particles effectively, the Martian surface receives significantly elevated levels of ultraviolet and cosmic radiation. Long-term exposure poses serious health risks. Any habitat for human life would need to be shielded. Some researchers have proposed using water ice as insulation material, constructing dome structures whose walls contain water that simultaneously absorbs radiation and provides a reserve for colony use. Others have suggested building underground, where the rock itself provides natural shielding. And yet Mars is not without resources. Water ice exists at both poles. More critically, evidence suggests that significant deposits of water ice exist beneath the surface at lower latitudes as well. One region that has been identified as a candidate for early settlement is called Arcadia, a broad, relatively flat plain northeast of the giant shield volcano Olympus Mons. The terrain is favorable for landing large vehicles. The latitude is close enough to the equator to receive reasonable solar energy, and the subsurface is believed to contain accessible water ice deposits. Water, on Mars, is not just for drinking. Split into its component atoms through a process called electrolysis, water produces oxygen for breathing and hydrogen for fuel production. It is, in a very real sense, the foundation of any self-sustaining colony. SpaceX's vision for building that colony relies heavily on what engineers call in-situ resource utilization, the practice of using what is already on Mars rather than shipping everything from Earth. A working propellant production plant would convert atmospheric carbon dioxide and subsurface hydrogen into methane and oxygen, the same fuels that power Starship. Solar panels, paired with large battery storage systems, would supply the electricity to run this and every other critical system, around the clock. Roads and landing pads would be constructed from materials mined and processed on site. Some researchers have proposed a construction material nicknamed biocrete or astrocrete, a composite made from human urine mixed with Martian regolith that preliminary studies suggest could produce a material stronger than standard. Earth concrete, human waste, in this scenario, becomes a building material. Even human remains, the biological outputs of a living colony, become inputs for agriculture and infrastructure. What if every component of a Mars colony, down to its construction materials, had to be designed around what could be found or made on the planet? That is not a hypothetical question. It is the engineering reality SpaceX's planners are attempting to address. Here is a number that rarely appears in the public conversation about Mars colonization: 5,000. According to the research used to inform SpaceX's planning, a minimum of approximately 5,000 people are required on Mars for a colony to have a realistic chance of long-term survival. The reasoning is genetic diversity, specialization of labor, and redundancy enough people to carry the knowledge and skill sets needed to maintain complex systems, even when some are lost. A colony of 100 people can be wiped out by a single equipment failure. A colony of 5,000 has resilience. SpaceX's stated goal is not 5,000 people, it is 1 million. To understand what that means in practical terms, consider the launch windows. Earth and Mars align in a way that allows efficient travel approximately every 26 months. That is the rhythm of the solar system, fixed, unavoidable, and not subject to business planning. Miss a window, and you wait 2 years. SpaceX's proposed architecture involves a fleet of over 1,000 Starship vehicles. Each carries 100 people. At one launch window every 26 months, with multiple vehicles launching per window, the mathematics of reaching 1 million people stretch over decades. The estimated cost per Starship vehicle stack is approximately $560 million, getting the per-person ticket price down to $200,000. The stated target requires achieving extraordinary economies of scale across manufacturing, launch operations, and fuel production. For context, the current estimated cost of sending a single person to Mars using conventional technology has been placed at roughly $10 billion. The goal represents a reduction in cost by a factor of approximately 50,000. Some researchers describe the timeline as stupendously unreasonable. Others argue that reusable rockets were once considered equally unreasonable, and that SpaceX has already demonstrated reusability that the industry once considered impossible. The economics of the company itself are also shifting. As of 2026, NASA constitutes less than 5% of SpaceX's projected revenue. The vast majority comes from Starlink, the company's commercial satellite internet system, which now operates at global scale. SpaceX is reportedly planning a potential public offering in 2026 that could raise an unprecedented sum, valuing the company at approximately $1 trillion. The company has also completed an acquisition of Musk's artificial intelligence venture in a deal that valued the AI company at $250 billion. The financial picture is complex. Mars is a long-term project in a company that is also operating satellites, launching government payloads, and expanding across multiple industries simultaneously. Whether the Mars program retains its priority in that context is a question the data does not yet answer. Now, set aside the engineering. There is a question that is harder than both. Who is in charge on Mars? SpaceX has already provided an answer, of sorts. The company's Starlink service terms of service, which apply to activities on Mars, contain language stating that parties recognize Mars as a free planet and that no Earth-based government has authority or sovereignty over Martian activities. SpaceX's stated governance model for a Mars colony is direct democracy and self-determination, not representation, but direct participation by the colonists themselves. But here is what international law currently says. The Outer Space Treaty of 1967, which the United States has ratified, prohibits any nation from claiming sovereignty over a celestial body. It does not explicitly address private claims or private governance. Legal scholars who have examined the question note that SpaceX, as an American corporation, remains subject to American law. The crew aboard any registered Starship would be subject to the jurisdiction of the state in which the vessel is registered. Some legal scholars argue that Mars colonists could eventually claim independence under the principle of self-determination, a recognized concept in international law. Others argue that under current frameworks, forming a new nation on Mars would constitute a territorial claim, which the Outer Space Treaty explicitly forbids. This is not a settled question. It is an open one, and the answer, when it comes, will have implications that stretch far beyond Mars. There are also questions about planetary protection. Mars may not be an empty planet. The question of whether microbial life exists, or once existed, beneath its surface remains one of the most significant open questions in science. Any human presence on Mars risks contaminating that potential biology with Earth microorganisms, some of which are extraordinarily resilient. Research has shown that certain bacterial spores can survive exposure to the harsh conditions of space for extended periods. At surface level on Mars, the radiation, chemical composition of the soil, and absence of liquid water make the surface lethal to most known life. But below the surface, in possible liquid water reservoirs, conditions may be more hospitable. The international scientific body that governs planetary protection standards, the Committee on Space Research, has issued guidelines that require enhanced biological cleanliness for missions to Mars. Human missions, which are biologically impossible to sterilize completely, represent a significant complication for those guidelines. What if the first humans to reach Mars inadvertently carry with them the organisms that end any chance of finding Martian life? That question has no easy answer. Here is something rarely discussed when Mars colonization is described in engineering terms. The people. A first-generation Martian colonist would live in approximately 50 square meters of personal space, not as a temporary measure, as a long-term reality. The psychological research on confined, isolated environments is extensive. Studies of analog environments, Antarctic stations, submarine deployments, long-duration simulation missions document the effects of isolation and confinement, dysphoria, social friction, psychosis in extreme cases, and in some documented instances, suicidal thinking. A Mars colony would be separated from Earth by a communication delay of between 3 and 22 minutes each way, depending on orbital position. A two-way conversation would take between 6 and 44 minutes at minimum. In crisis, there is no real-time consultation with Earth. Every decision is made by the people on the ground. The psychological demands of that environment, the isolation, the boredom, the homesickness, the confinement, the awareness that evacuation is not an option, have no parallel in any existing human experience. There are also questions that science cannot fully answer. Genetic diversity within a small founding population is a real concern. Children born on Mars would be born into a life they did not choose, with limited space, limited resources, elevated health risks, and no possibility of leaving on a whim. The ethical dimensions of bringing children into that environment have been raised by researchers, though the debate remains unresolved. There are debates about reproductive policy in environments where medical resources are severely constrained. There are questions about how mental health crises would be managed with no external evacuation option. Some researchers believe these challenges are solvable through careful selection, preparation, and community design. Others argue that the ethical dimensions have not received adequate serious attention relative to the engineering. And then there are the critics. Lord Martin Rees, the British Astronomer Royal, has described the idea of large-scale Mars colonization as a dangerous delusion, noting the immense physical and psychological challenges involved and questioning whether the benefits justify the costs relative to unsolved problems here on Earth. Former President Barack Obama noted that Mars may prove more inhospitable than Earth in the aftermath of a nuclear war. Others have argued that SpaceX's timelines are, to use the language of one critic, stupendously unreasonable, driven more by ambition than by verified capability. These critiques do not come from ignorance. They come from people who have studied the problem carefully. Here is what we know so far. SpaceX has built a rocket that has demonstrated extraordinary capability. Starship has achieved the trajectory its engineers designed for it. Both stages have demonstrated controlled landings. The Sabatier chemistry that would allow fuel production on Mars is established science. The human body can survive long-duration spaceflight with difficulty, with cost, with countermeasures that are imperfect and still evolving. Mars has water ice. It has carbon dioxide. It has solar energy at a workable level. The raw materials for a colony's survival exist on the planet. And the plan, as of February 2026, has been delayed. The next Mars launch window is years away. The lunar missions have taken priority. The self-sustaining city on Mars that was once projected for around 2050 now exists on a timeline that stretches into the mid-30s at its earliest and beyond. Here is what the data suggests, but does not confirm. That the engineering problems are solvable. That reusable rockets can drive costs down far enough for mass transport to Mars to be economically viable. That a rotating habitat can sustain human health over a multi-year mission. That the chemistry of Mars can sustain a colony's fuel and food needs. Some researchers believe all of this. Others argue that critical variables remain untested at scale, and that history is full of engineering programs that were technically sound in outline and catastrophically underprepared in execution. And here is what remains genuinely open. Whether human life on Mars is sustainable over generations, whether the legal frameworks governing a self-governing Martian colony can be constructed before the colony needs them, whether Mars still harbors life of its own, and if it does, what obligations that creates for any humans who arrive. Whether the children born on Mars, if they are born there, will think of Earth as home or as a distant story. The ambition is real. The engineering is real. The obstacles are equally real. What we cannot know, from where we stand in February 2026, is which of these forces will ultimately determine the outcome. For now, the plan exists in the space between what has been proven and what has been promised. The machines are being built. The windows open every 26 months, patient as clockwork, indifferent to schedules. The planet turns 140 million miles away. And the question it poses is one of the oldest the human species has ever asked. How far is far enough?